The topic of this lecture is basics of memory management, having to do with how the RAM memory in a computer system works and how the operating system manages it. Previously, we have been discussing about virtualization, and we continue this memory management topic continues on the idea of virtualization, but with the distinct difference that previously we have been talking about how to virtualize the CPU, how to provide the individual programs, processes, their own context of execution. Now we start to talk about how to provide those processes their own memory space. But before going into that, let's consider a little bit where we are and how we have come here. So where are we at? At this stage, we have an idea about how the computer executes instructions, how it executes program code. We also have an idea about how the computer system selects the next operation to execute. In essence, which program should be running. This was the whole discussion on scheduling and processes. And previously, we also looked at assembly code. So we know what the actual instructions the CPU executes are and how they look like. So the next step here is to consider how do we store those processes into the system memory, how to make them all fit, how to make them play among each other nicely. So in general, the main memory or random access memory is a sequence of memory slots numbered from 0 onwards. And how many memory slots we have depends on how much RAM memory you have. If we have 8 gigabytes of memory, then the first memory slot is at 0, and the last memory slot is at is numbered 8,589,934,591. Usually when talking about operating systems and how memory management works, and even in our recommended textbook and some examples that we have here, we speak about very small numbers, something that's definitely not 8 billion memory slots, but something like 16,000 or 32,000 or even less. The reason behind this is for simplification. The basic principles behind how everything works remain the same. It's just that there is, in practice, in modern computer system, there is much more space and much more memory slots. Anyway, the basic problem of memory management is how to distribute this memory space in an efficient way so that each process gets allocated its own space, and also how the operating system gets allocated its own space. Remember, the operating system and its processes are also program code on the very basic level, and they need to be executed at some point, and they need their own context of execution, they need their own memory space. And again, I have mentioned this earlier, but right now we presume that we only have one processor and multiple processes or multiple programs sharing that one physical CPU. But of course, in real life, this might or might not be true. But usually, for clarity's sake, it is easier to think of these problems in a way where we have one physical processor and multiple programs. But of course, in real life, this scales up so that it's also possible to schedule and manage processing on multiple CPUs at the same time. On a very high level, we would probably want to see something like this. So if we were to draw the memory space as a sort of film or disk, we would probably do something. It would probably look a bit like this. So usually when we draw a memory segment as a picture, the beginning of the memory is at the top, and then it the memory slots grow toward the bottom. So the beginning is at the top of the picture, and the end is at the bottom. And like discussed, we would ideally want to have some segment of the memory here reserved for the operating system, and then the rest of the memory for whatever program is currently being executed. And if we have enough memory, we could even store every single program that is on the computer system into RAM, and sometimes that might be possible. Oftentimes though, we have to do a little bit of swapping. So swapping basically means switching things from the RAM memory to the disk because of the physical limitation that we can't fit every single program and its context into RAM memory. Anyway, all of this starts with the operating system. So at the start of the memory sector, the beginning of any disk or memory device is called a sector. The operating system, when it boots up, it loads its own subroutines and data onto this start sector, and the rest of the memory is then divided among the different processes that exist. The remaining free memory space for programs after the operating system has allocated its own memory page here is then divided more or less evenly. So it's split into these blocks, which are called pages, by the way, which are then allocated to each process. And the operating system keeps a record of what process is in which physical location. The processes are only meant to work and access their own memory region. And this is for the sake of security. So what would happen if an application process gets to write in some other program's memory space, or let alone the operating system's memory space? That, from a security standpoint, by the way, is what is called a buffer overflow. So the memory from one process leaks into the space of another, meaning the buffer gets overflown. And that could have a really bad effect on how these processes behave. One program could even crash another or do some other malicious things. Of course, having the memory divided into many blocks means that memory use is not especially efficient. So we might end up with some segments in the memory which are currently not in use. And if we were to somehow divide memory space very efficiently, then we would have all the allocated memory space in a much neater package, and then we would have the memory space that's not yet allocated down here at the bottom. But this, of course, in real life often doesn't happen. I suppose the takeaway from this is that behind the scenes, the operating system also can do a little bit of memory space cleanup. It can try to compact the memory to be used as efficiently as possible. This is more of a side note though, so it's just something to keep in the back of your mind, that when we allocate blocks of memory, the allocation of memory may be less than ideal. The cleanup of memory is the process that is called defragmentation. And basically what it means is the operating system takes care of that memory, takes care of the memory so that it doesn't get too fragmented. It can use memory reservation algorithms like best fit, worst fit, first fit. These are the things that we explored in the first assignment with the Jack operating system. So you will remember these best fit and first fit algorithms. Anyway, defragmenting basically means calculating new, more optimized memory locations or moving data within the memory and updating these records. Or in the case of the memory being really full, we need to move some of the data onto the disk drives for some period of time when it is needed. Writing to the disk is of course slow and inefficient, but it makes it possible for you to actually handle more data than what memory space you have remaining. The idea of splitting memory into slots is actually called paging. So one slot is what is called one page or one page frame. The idea behind this division is that we simply divide memory into slices, and then it's easy for the operating system to keep track of what page or page frame is used and what isn't. And the idea here is that each page is the same in size. So for example, here on the right, there is a page frame number 0 here, and it's exactly, is this now 16 bits or 16 bytes long, whatever, depends a little on what the page frame size here is. And all of the other page frames are exactly the same size as well. So this is what we mean by slicing the memory into pages. The advantage of this is that it's easy to move pages from one location to another. So for example, if we wanted, we could move page 2 here to this unused memory page, which is page frame 4 here. It's also easy to keep track of what pages are given to what processes in the memory space, and keeping track is relatively simple because, well, all we need is some kind of table which contains this paging information. So basically paging information is where some process is or where parts of processes are stored in memory, or in practice what pages are assigned to which process. The idea of paging is fairly relatively straightforward, and just to bring in a few real-world complications to this, let's consider what is it that a process actually needs to load into memory. Well, all of the program code for one, so the program code might end up taking at least one page or one page's worth of memory. So the program code, basically the code segment where all the program instructions live. But in addition to this, the operating system actually reserves some additional memory, some additional page frames. So it's everything all the way up to here. So you will notice there is something called a heap in one page frame, a stack in another page, and then there is a number of pages which yet remain unallocated. Now, what are these extra memory segments here? So the heap is basically memory that's reserved for all the variables that you have in the program. If you assign some value to a variable, that value needs to be stored somewhere. So that is what is called the heap. And the more variables you have, the bigger the heap becomes. Or well, the more memory pages the heap needs, the operating system needs to reserve for the heap. The stack, on the other hand, is the program's execution time memory. So sometimes we don't know in advance how much some data structure is going to require space in the memory. So that's why there is a pre-allocated stack which will contain all the memory that the program needs runtime. And then this stack grows upward. So once we load and save or need to save more data, the stack becomes larger and larger. And the idea is that there is some free space in between for the stack to grow. All of that about paging is basically just the fundamentals of how memory segmentation works. And why we have pages, well, that has to do with protecting processes and their memory spaces. The bottom line with this is that the same computer needs to be able to run 2 or more processes at the same time. And if you recall what the process is, once more, it's the runtime execution of a program. Program is different to a process. Anyway, processes must be kept safe from each other. The execution of one process cannot interfere with another one because, as discussed previously, it could have very bad consequences. For this reason, to keep processes safe, we need some mechanisms and protocols. A mechanism is a way to do something. A mechanism is a tool. A mechanism does something. So, for example, paging is a tool. A protocol, on the other hand, is a rule set that specifies how to use mechanisms. And protocols usually are the way to achieve safety for the processes. So the goal is here to protect, in order to protect processes, to stop programs from crashing the operating system, to stop programs from crashing each other, and to stop parts of the operating system crashing each other or other programs. Keeping those goals in mind, there exists a couple of possible mechanisms to achieve all of this. One mechanism, one tool is called address translation. And another tool is called separate user mode from the operating system mode. The protocol or rule set with which we need to use these tools could be fairly simple, something like keep programs from accessing memory space of other programs or the operating system. So in other words, a program is only allowed to access its own memory space. So what exactly is address translation then? So address translation is a mechanism which virtualizes the RAM. So address translation is a way to provide virtual RAM memory for application programs. So from the program's perspective, they can see memory, but the memory they see is not the real physical memory, rather it's virtual memory that the operating system provides for them. What a single program or single process sees is something like this, where they see their program code and starting from the beginning of the memory segment. And you will remember in the previous picture, which looked the same, we had the operating system code in the beginning of the memory segment. Now this is the idea of virtual memory. So for the program, let's make it seem like this virtual memory is everything that exists. So if the program itself cannot see any other memory spaces, then it can't possibly access any of them. So that is basically what the operating system wants to do. This way, this program thinks it's the only thing running on the CPU. The code of and data of the operating system is unreachable by the program because it's invisible, and also code and data from other programs is unreachable because they are also invisible. So in essence, this virtual memory concept is making it look like the program is the only thing running on this computer system. In practice, the application programs see some memory addresses. For example, from 0 onwards to whatever is the last remaining memory slot. And the program thinks it's using these addresses. But in the physical memory, the situation is completely different. That is where a operating system component called the Memory Management Unit, or MMU, translates these addresses. So the address the program sees gets translated into a real physical memory address, and it can actually be physically located somewhere else. So the MMU knows which memory pages are used by what processes and in what order, and then it translates those memory pages into virtual memory addresses. So real physical memory addresses are different from the ones that programs see. Programs see these fake virtual addresses instead. And every time a program needs to access something in memory, that memory address where the writing or reading takes place is put through what is called memory mapping. So there is a memory address table stored by the memory management unit, which maps virtual memory addresses to physical memory addresses. And at this point, it's good to keep in mind that this address translation has to be really efficient, because otherwise it would unnecessarily slow down the execution of application programs. So basically what happens in address translation is that the CPU points to some memory addresses. That is what happens here. And then the memory unit, memory management unit, or magic memory unit, however you want to call it, translates those addresses to physical real memory. And then this memory management unit makes sure that those virtual addresses are mapped correctly to the physical addresses, basically leaving this black box between the virtual addresses and physical addresses, so that programs only see the virtual addresses. Therefore, how the physical page frames are allocated between different programs can be more complex than how it seems to a single program. So for example, let's say we had one program on the left, one program or process on the right, and their individual pieces of code and data are mapped by the memory management unit to real physical page frames. And those page frames can then be distributed all around the physical memory space. So for example, here the physical or the virtual code segment for process 2 is here in the beginning of its memory space, but actually when it's mapped, it turns out it resolves to a page that is actually the last one of everything that you see here in this picture. The bottom line with address translation is that programs indeed have their own memory space in which no other processes are allowed in. Memory spaces do not overlap except if we make them overlap. There is sometimes a need for two programs to share data, which is not something to discuss further at this part, but just so you know, most often programs do need to communicate with each other, and shared memory is one of those ways in which they can communicate. Memory addresses in the real physical world cannot overlap. This is the mechanism that prevents one process accessing runtime data of another. And also there are more security reasons to keep processes from being able to access each other's memory space. For address translation to make sense, the memory address translation table needs to be under the operating system's control and the operating system's control only. So remember this picture that we looked at a few lectures ago about what happens when there is an interrupt. So we talked about the division between a user process mode and kernel process mode. So as discussed previously, the scheduler also will occasionally switch the context of execution back to the operating system if the user processes require some favor from the operating system, or at other times when the operating system needs its processes to continue as well. One of the times when the control of execution switches back from user processes to the kernel is when we have to do address translation. So address translation is always done in the kernel level and not in the user process level for security reasons again. This is in practice done by having at least two levels of privilege in execution, and most computer architectures have at least two. The X86 platform, which is the physical processor architecture for most PC computers, there are actually 4 modes, but we need at least 2. We need the kernel mode and the user mode, but there can be more. There can also be modes that are between kernel mode and user mode, or there could be a mode for code execution which is below user mode, so even more restricted than user mode. But at least 2 is necessary for address translation to work. The reason why we need a user mode and a privileged kernel mode is because some of the hardware resources need to be limited to the operating system's use only. In practice, some instructions can and are reserved for the operating system's use only, and memory translation is one of those. The memory address table can only be accessed by the operating system and therefore only by the memory management unit. There exists also certain machining instructions that cannot be used by user mode programs. For example, trying to access the address table can't be done, or accessing memory space outside of a process's allocated page can't be done either. If you were to try and you get an error, the operating system will not allow you to do that. And that error is either a page fault or a segmentation fault. If you have ever run programs in the Linux command line, or even programmed on the Linux using the Linux operating system, you may have seen these errors. So now you also know what causes them. So it's basically a program not using memory quite right and trying to access the memory space outside of its allocated area. And lastly, what were the key concepts discussed in this lecture video? So we talked about the basic principles of memory management, so basically the concept of virtualizing memory. And that virtualization is provided by 2 mechanisms, paging and address translation. And then in order to control the execution of different programs and switching between privileged kernel code or operating system code and application program code, there needs to be a separate privileged kernel mode for operating system processes and user mode in which user space programs are executed, and these 2 do not clash for the sake of providing that secure sandbox for application programs to run in, whereas the operating system, it has a few more liberties to run on the CPU.